Now I want to look at what happens when I have functions that are dependent on two or more independent variables where I have to use the chain rule. Keep in mind that there are different levels of functions here with variables that show up at each of the different levels. I can have multiple variables at each level. For example, I could have z, which could be a function of x and y, and each of these intermediate variables can be functions of s and t. So I'm going to show you a tree diagram that gives me the hierarchy of how these functions relate to the independent variables and the intermediate variables. I start with z at the top, and I draw an arrow down to a point x. This is my z function to my x function, showing that z is dependent on x. I draw another arrow to the y function, showing that z is dependent on y. Now from x, I draw an arrow to s, showing that x is dependent on s, and I draw another arrow to t. Under y, I draw an arrow to s and another to t. The tree diagram illustrates that x and y are directly dependent on s and t, and that x and y are my intermediate variables. They lie between z and the s and t. It also shows that z is directly dependent on x and y. But because I can go through x and y to get to s and t, my z will ultimately depend on both s and t. When a function has two intermediate variables that each rely on two independent variables, I'm going to use partial derivatives for every term. So that I have the partial derivative of z with respect to s will be given by the partial of z with respect to x times the partial of x with respect to s, plus the partial of z with respect to y times the partial of y with respect to s. The partial of z with respect to t will be given by the partial of z with respect to x times the partial of x with respect to t, plus the partial of z with respect to y times the partial of y with respect to t. I can also extend these ideas to more than two independent variables, keeping in mind that there are different levels where these variables might show up. So for example, I might have a function w that is a function of x, y, and z, and each of these intermediate variables could be functions of both s and t. My tree diagram here starts with w at the top. I draw an arrow to the x function. I draw another arrow from w to y, and a third arrow from w to z. From x, I draw two arrows, one to s and one to t. The same thing for y, an arrow that goes directly to s and an arrow that goes directly to t. And again, the same in z. I have an arrow that goes directly from z to s and another arrow that goes directly from z to t. This illustrates the levels at which my functions and variables show up, and my derivatives are going to be partial derivatives, again because w depends on three variables and x, y, and z each depend on two variables. So I will have the partial of w with respect to s will be equal to the partial of w with respect to x times the partial of x with respect to s, plus the partial of w with respect to y times the partial of y with respect to s, plus the partial of w with respect to z times the partial of z with respect to s. And my partial of w with respect to t will be given by the partial of w with respect to x times the partial of x with respect to t, plus the partial of w with respect to y times the partial of y with respect to t, plus the partial of w with respect to z times the partial of z with respect to t. Now suppose I have a function w that depends on only one variable, let's call it z, but z depends on two variables, x and y depend on the variable t. This tree diagram is a little bit different, and these diagrams can really help you clarify when you will use ordinary derivatives and when you will use partial derivatives. So I'm going to set it up so that w has a single arrow pointing from w to z. From z, I know that z depends on x and y, so I have two arrows from z, one pointing to x, one pointing to y. And x and y both depend on t. So I have a single arrow from x to t and a single arrow from y to t. The function w at the top depends on z only, so this rate of change will be an ordinary derivative, dw dz. The function z depends on x and y, so this rate of change will be partial derivatives. And the functions x and y depend only on t, so these rates of change will be ordinary derivatives. I'm going to get dw dt is equal to dw dz times the partial of z with respect to x times dx dt plus dw dz times the partial of z with respect to y times dy dt, and this is going to be equal to dw dz times the quantity the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. And you'll notice that ultimately w depends only on the independent variable t, so that is an ordinary derivative. So let's work an example. I want to find zs and zr when z is given by sine of x times cosine of 2y, where x is equal to s plus t and y is equal to s minus t. The partial of z with respect to s is equal to the partial of z with respect to x times the partial of x with respect to s plus the partial of z with respect to y times the partial of y with respect to s. I have all partial derivatives because z depends on x and y and y both depend on s and t. The partial of z with respect to t will be equal to the partial of z with respect to x, the partial of x with respect to t, plus the partial of z with respect to y times the partial of y with respect to t. I'm using all partial derivatives here because z depends on two variables, x and y each depend on two variables, s and t. Now I need to find the partial of z with respect to x. This is given by cosine x times cosine 2y. The partial of z with respect to y is given by negative 2 times the sine of x times sine of 2y. The partial of x with respect to s is 1, and the partial of y with respect to s is 1. The partial of x with respect to t is 1, and the partial of y with respect to t is negative 1. This means that zs is given by cosine x times cosine 2y minus 2 sine x sine 2y. I'm going to plug s plus t in for x and s minus t in for y. I get cosine of the quantity s plus t times the cosine of 2s minus 2t minus 2 times the sine of the quantity s plus t times the sine of the quantity 2s minus 2t. zt will be given by cosine x cosine 2y plus 2 sine x sine 2y. Again, I plug in s plus t for x, s minus t for y. I get cosine of the quantity s plus t times cosine of the quantity 2s minus 2t plus 2 times the sine of the quantity s plus t times sine of the quantity 2s minus 2t. Let's do another example. I want to find dz dt for z is equal to the natural log of x plus y, where x is t times e to the t and y is e to the t. And I want to use two methods to do this. The first method is to replace x and y with their respective functions of t and then differentiate. And the second is to use my chain rule approach. For the first one, I'm going to directly substitute t e to the t for x and e to the t for y in my natural log. This means that z is equal to the natural log of x plus y becomes z is equal to the natural log of the quantity t e to the t plus e to the t. Now I'm going to simplify this before I try and take a derivative. This becomes the natural log of the quantity e to the t times t plus 1. I can use my log rules to break this product up into the sum of two logs. I get the natural log of e to the t plus the natural log of t plus 1. This simplifies to t plus the natural log of t plus 1. Now I take the derivative of z with respect to t using my simplified form. dz dt is equal to 1 plus 1 over t plus 1. Finding a common denominator and simplifying, I get t plus 2 over t plus 1. Now I'm going to use the chain rule. In other words, I want to find dz dt, which is equal to the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. The partial of z with respect to x is given by 1 over the quantity x plus y. dx dt is given by e to the t plus t e to the t. This simplifies to e to the t times the quantity 1 plus t. The partial of z with respect to y is 1 over the quantity x plus y, and dy dt is given by e to the t. This means that dz dt will be given by e to the t times the quantity 1 plus t over x plus y, plus e to the t over x plus y. I'm going to simplify that. That gives me e to the t times the quantity 2 plus t over x plus y. When I plug in t e to the t for x and e to the t for y, I get e to the t times the quantity 2 plus t over the quantity t e to the t plus e to the t. Factoring e to the t out of the denominator and canceling common terms on top and bottom reduces this to t plus 2 over t plus 1. I get exactly the same result regardless of the method I choose. Be careful. If you are asked to solve using the chain rule, be sure and use the chain rule. If you're asked to solve using another method, use that. If you're given the task of solving this using the chain rule, then go back and use the direct substitution and differentiation method as a check of your work. So now you get to try it. Pause the video and find zs and zt when z is equal to xy minus 2x plus 3y, and x is equal to cosine s, y is equal to sine t, and do this using the chain rule. When you're ready, restart the video to check your understanding. In this case, I'm finding both zs and zt, and I'm doing both of them by using the chain rule, so that dz ds will be given by the partial of z with respect to x, dx ds, plus the partial of z with respect to y, dy ds, and dz dt is given by the partial of z with respect to x times dx dt plus the partial of z with respect to y, dy dt. The partial of z with respect to x is y minus 2. The partial of z with respect to y is x plus 3. dx ds is negative sine s. dy ds is 0. This means that dz ds will be equal to the quantity y minus 2 times negative sine s plus the quantity x plus 3 times 0, which gives me the quantity y minus 2 times negative sine s, or sine s times the quantity 2 minus sine t, where I've simply replaced y with sine t and distributed the negative sign. dx dt is 0, and dy dt is cosine t. This means that dz dt is the quantity y minus 2 times 0 plus the quantity x plus 3 times cosine t. This simplifies to the quantity cosine s plus 3 times the cosine of t when I plug cosine s in for x. Be sure and let me know if you have any questions about working with the chain rule and partial derivatives.